Hello, in this lecture, we'll see how to use TensorFlow to gradient tape. It is a means of accessing the gradients for each node, and then you can create for many purposes, such as your custom loss function and all. So let's see how this works. So gradient tape. So first, we'll import the TensorFlow library. Okay, let me actually get a faster GPU. So if I go to change runtime type, the GPU, okay, all right. So now let me just run it. Okay, so it's I'm just checking the version because I want to have a TensorFlow version higher than 2.0, which these days it usually is. It's 2.8 right now. So first, simple stuff, evaluate the derivative. So let's suppose that there's a variable x. I assigned a value of 3 as a tensor. So it's a TensorFlow tensor type. And then how I use it, the gradient is that, well, in the formula what I'm interested, let's say y equal x squared, TF, the TensorFlow gradient tape as tape, okay? And then have the function. So this recognizes I want to use the x here and all in a gradient. And what actually I want to gradient is the tape that here of the gradient of y on x. Okay, so which I call it dy underscore dx, print it, and then I'll delete and release these tensors. So let's see. It gives me 6, isn't it? The x squared derivative is 2x, and x happens to be 3. So 2 times 3 is 6. So it does compute. So this is a simple way to illustrate how to evaluate the derivatives. I highly recommend go to Google and check gradient tape, the TensorFlow gradient tape, and they have many, many different kinds of options that you will find what you need most of the cases. So here's an example of how we do it in linear regression, for example. First, the standard stuff. I just create a NumPy array of 0 to 10, 11 data points, and then a function of y equal 2x plus 1 plus some noise, random number noise. So, it's a 1, 3, 5, 7, you know. So these are the funds. So it's a straight line 2x plus 1, but some noise around it. Okay. So, and let's have a regression parameter. Suppose that we don't know the 2 and 1s here. So let's have a and b to represent the intercept and the slope of it. And I'll have to define a loss function for the regression. In regression, we do, well, here I did for just the absolute difference. I could have done a square loss, but let's just do a simple absolute loss. So if there's a y and predicted y, I'll just take the difference in absolute value and I'll minimize it. So it's not minimize square error, it's actually minimize the least absolute error. Okay, so again, the same thing. So here's just one step of, so one batch of data coming in. And what I'll do is that I ask the gradient tape as tape. And what's the formula? First, ax plus b. So this is the slope and this is the intercept. And I get the prediction. And then against the real data and the prediction, here's the loss function. I take the absolute difference, and that is my loss. And I want to minimize it. So how do I do this? First, I get the gradient with respect to a and b, and then I will assign this, update the variables of a and b to minimize this absolute error for each data point c. Training the loop, repeat the data set 10,000 times. So I'm calling this one step 10,000 times, and then let's see what the resulting a and b's turn out to be. So y equals ax plus b, and let's see, it is running it the data set, the whole data set 10,000 times. So it may take a few seconds to run it. Okay, so it's done running. So it's 1.99x plus 1.15, which is pretty close to the true, which was y equal 2x plus 1. So in the absolute error, you could have done it. Of course, I could have defined it in the square error, and it will give me a slightly different answer. All right, so this is how you use it in regression. And as you can see, the gradient is very useful in finding this, isn't it? Because we're doing some sort of back propagation to update it. So, and here's an MNIST classification. So let's just import the libraries. And as usual, I load the data, scale it, reshape it by 784 and 60,000 for the trained data. And I'll compute a categorical data. So the 0 to 9 digit will be 10 dummy variables. And then batch size of 128 and 25 epochs. I'll just use a very simple fully connected neural network layer, 784 to 512 to 128. And at the very end, I'll have 10 softmax nodes. I'll use Adam optimizer. And here's the real thing that I want to talk today. So for a single batch of data, I'll use the GradientTape as tape. So this repeats all the time, isn't it? And give me the function what I want to compute the derivative of. So prediction is the model. So here's the neural network model. X comes in, the model predicts a Y, and then the loss, I want to have it categorical cross entropy function here. That's my model loss. For that, we will compute the gradient, model gradients, and then with the Adam optimizer, so I'm doing some kind of back propagation of update the model gradients based on the model gradients, all the trainable variables. So this is a trick, isn't it? The model, all trainable variables will find all the weights inside this neural network, and it will update all these weights. Okay. All right. So here's training the loop 25 times. So this will have 25 bars coming up. It's a first data batch of data running, right? And then the second batch of data running, we'll do this 25 times. And let's come back when it's done running. Okay, it's done training the network. So let's calculate how accurate it is using the test data. So I'll compile the model just for evaluation, and then model evaluate of the X test and Y test and see how accurate it is. And we get about 98% accuracy in the test data. So it is pretty good, isn't it? So you can see that how GradientTape is used to help back propagation. So it's a very useful function. Someday, if you want to design your custom losses and your own algorithm, this will come in handy. Thank you for watching this video.